Now, the module 2, in continuation with the module 3, powder metallurgy, that is part 2, will be studied. That is chemical method of powder production techniques we will be studying now. That is, the chemical reduction involves chemical compound, mostly, most frequently an oxide, but sometimes a halide or other sort of the metal. This may be carried out from the three different states. The first one is from solid state, from gaseous state, and from the aqueous solution. From the solid state, as in the reduction of iron oxide with carbon of or of tungsten oxide with the hydrogen. The sponge iron powder produced by the Hagnan's process is a typical example of this production method. This is a batch process in which the ground ores does not move during reduction but is in static, in contrast to other direct reduction processes which are continuous. The Hagnan's process is based in the use of quite pure magnesite ores. The iron ore is reduced with a carbonaceous material. The figure shows the steps involved in producing such powder. The ore is ground to a particle size distribution determined by each of the desired iron powder. The ore powder is placed in the center of cylindrical ceramic containers, sagers made of silicon carbide, surrounded on the outside by a concentric layer of a mixture of coke and limestone. The sagers are placed in the layer upon cars, which are pushed through a fuel-fired tunnel clean. The carbon monoxide produced from the coke reduces the ore to iron. Total reduction time of the order of 24 hours at a reduction temperature of 1200 degrees centigrade. The limestone serves to bind any sulfur in the coke and prevent its contamination or contaminating the iron. The sponge iron is mathematically or mechanically removed from the sagers ground and the resulting powder magnetically separated from the impurities. In a final reduction, the powder is carried through a continuous furnace in hydrogen atmosphere on a belt made of stainless steel. The second one is the gaseous state. As in the reduction of titanium tetrachloride vapor with molten magnesium, the well-known roll process. The roll process, as a mature technique, has been developed for 7 decades and is operated in industrial large scale. The process includes several steps: carbohydration to produce titanium tetrachloride, titanium tetrachloride purification, the reduction of purified process includes several steps: carbochlorination to produce titanium tetrachloride. So, the reduction of the purified titanium tetrachloride by magnesium, as well as the electrolysis of magnesium chloride generates by the reduction to produce metallic magnesium and chlorine. During carbochlorination, carbon and chlorine are used to react with titanium oxide to produce titanium tetrachloride and carbon monoxide and CO2 between 1073 to 1175 Kelvin. The following treatment: the impurities of the silicon iron aluminium, magnesium, and calcium, etc., are removed by the fractional distillation to generate carbon, titanium tetrachloride around 99% purity. The purified or the titanium tetrachloride is reduced by the molten magnesium between 1075 and 1175 Kelvin in the argon atmosphere to produce sponge titanium by the subsequent cooling and vacuum distillation to remove the magnesium and magnesium chloride in sponge titanium. Purer sponge titanium can be produced. Magnesium chloride obtained from the reduction of titanium tetrachloride is sent to electrolysis sector to produce chlorine and magnesium. The chlorine and magnesium produced are respectively used for chlorination of titanium oxide and reduction of carbon titanium tetrachloride respectively. So the third one is production of powder from the chemical method, that is from the aqueous solution, as in the precipitation of cement copper from copper sulfate solution with iron in the reduction of an ammonical nickel salt solution with the hydrogen under pressure. Low cost copper powder is produced from the solution obtained by leaching copper ores or copper scrap, where the precipitation of copper powder from an artificial solution of copper sulfate with iron is achieved. Large quantities of this cement copper are produced from the copper sulfate solution, which are the byproducts of the copper refining industries. Most of the cement copper is eventually melted and cast rather than used as powder for two reasons. First one, the cement copper produced as a byproduct is rather impure unless special precautions are taken. And the second one is the powder is quite fluffy. That is, it has a low apparent density, which is not satisfactory for many copper powder applications. To make the powder suitable, a furnace treatment, which would increase the cost, could be necessary. The nickel powder produced by Sherritt-Gordon process is the typically hydrometallurgy method for producing, in which reduction of ammonical solution of nickel sulfate with hydrogen under pressure of 1.38 megapascal and a temperature of 190 to 200 degrees centigrade in an autoclave is carried out. A nickel salt solution is obtained for leaching complex copper, nickel, and cobalt ores. Before the nickel is precipitated as metallic powder, the copper is removed from the solution by precipitation and sulfide. For the precipitation of the first nickel powder nuclei from the solution, the catalytic example, ferrous sulfate, is used. The very fine nickel powder nuclei are allowed to settle in the autoclave. The barren solution is decanted and a new batch of solution is introduced into the autoclave. The nickel powder nuclei are suspended in the solution by agitation, and the nickel in the solution is reduced with hydrogen at 1.38 megapascal and precipitated on the existing nuclei. The process, called densification, is repeated many times, say 15 to 50. Finally, the powder is removed from the autoclave, washed and dried. The process permits controls of the size and shape of the nickel powder being produced. Thank you.